All right, in this example, we have a weather balloon, and we're told that the volume of gas inside the weather balloon decreases by zero point 0.2 liters per millimeter of mercury of air pressure, right? So, as you would expect, as the air pressure increases, the volume of gas inside the balloon decreases. Okay, so this is actually a negative rate. Now, the air pressure decreases at a rate of 12 millimeters per mercury per mile of altitude, which again makes sense as as you increase altitude, there's less air pressure, right? So again, this is another negative rate. It's decreasing at a rate of 12 millimeters per mercury per mile of altitude. If the weather balloon is rising at a rate of 10 miles per hour, find the rate at which the volume of the weather balloon is increasing. All right, now, okay, we're just going to multiply these rates, sort of like we did at the beginning of this this section, right? We have 0.2 liters. I'll put a capital L for liters. Per millimeter of mercury, mmHg. All right, it's just a way of measuring air pressure is in millimeters of mercury. Now this is a negative rate, right? Because as the pressure increases, the volume will decrease, right? And vice versa. As the pressure decreases, the volume will increase. All right, so this is a negative rate. Now, the air pressure is decreasing at a rate of all right, it's decreasing at a rate of 12 millimeters of mercury per mile of altitude, right? Now, again, it's negative because it's decreasing as the altitude increases, the air pressure decreases. So it's another negative rate. And then the weather balloon is rising at 10 miles per hour. Okay, so just by using unit analysis, we can just multiply these rates, and you can see that what we'll get is liters per hour. Okay, now the negative times negative becomes positive. If we multiply all of this together, we'll end up with 24. And the units will be liters per hour. Okay, so at this point in time, the volume of the gas in the weather balloon is increasing by 24 liters per hour. Okay, so notice here we took three rates. We took three rates and multiplied them together. We took the rate of change of the volume with respect to pressure times the rate of change of the pressure with respect to altitude. I'll call it A altitude, lowercase a, and then we took the derivative of the altitude over time, right? With respect to time. We multiplied that all together and we ended up with the derivative of, well, essentially the rate of change of the volume with respect to time. Okay, now, so this is just the chain rule used a couple of times, and that's why it's called the chain rule, is because you can chain the chain rule. All right, so, and we can actually do this more than twice, right? We can put together as many rates as we want to and get a new rate. So this is what it looks like when we chain the chain rule, when we have three functions. All right, we have the outside function is f, inside that we have g, and inside of g we have h. Okay, so we have three functions all put together. Now, let's go ahead and just do example 8 at the same time here, because it's good to see how this works in general. So in example 8, we have sine squared of 5x to the third. Now, the first thing you probably want to do is, because you got to decide, okay, what's the outside function here? All right. So now when we have this notation where the sine is squared, we can rewrite that as the sine of 5x cubed and all of that squared. And I think if you rewrite it that way, it's easier to see what the outside function is, right? So it looks like my outside function is the square, because I'm squaring the whole sine function, and then inside the square is the sine, and then inside sine is a 5x cubed. All right, so let's break this down like we've done before. The outside function, we're just going to make z squared. Okay, it's the square function. And inside of that, the z is sine of u. Okay, because it's the sine of 5x cubed, but inside the sine we have this another function. So I'm going to break that down. U is equal to 5x cubed. Okay, so it's a composition of three different functions here. We have the square function on the outside with a sine inside of that, and inside the sine is the 5x cubed. So all we really need to do is take the derivative of each one of these things. dy dz is equal to 2z. dz du is equal to cosine of u, and then du dx is just going to be 15x squared. All right, and now we just multiply those all together, but we need to write it all in terms of x. Okay, so I'm going to write dy dx, right? dy dx, that's what I want to find, is the derivative of y with respect to x. So the first thing is 2z, but I have to replace z with what it actually is, which this is the sine of u. But again, I want to write everything in terms of x, so it's going to be the sine of 5x cubed. Actually, I don't really need this parenthesis here, right? I can just write 2 times that. Okay, so all right, so I have 2 times the sine, 2 times the sine of 5x cubed, and then I'm going to multiply that by the dz du, which is the cosine of u, but u is 5x cubed, and then I'm going to multiply by du dx, which is 15x squared. All right. Now, if you wanted to clean it up, you could make this into, I would probably write this as 30x squared, and then times sine of 5x cubed times the cosine of 5x cubed. All right, so there is one example of using the chain rule more than once. We chained the chain rule in that example. All right, so that's all I have for this for this section. That's an awful lot, but I'll see you in class.